Hi everyone, welcome back to the Green Chemistry Connections webinar. We are thrilled to have you gathering with us virtually from all over the world today. Today's presentation will feature Dr. Edigunder Pusami and Professor Irv Levy. We have more attendees joining us and we will be conducting a poll, so let us see a little bit about yourself. So I'm going to launch a poll now so that you can tell us a little bit about where you're joining us today from. So the poll is now open. You can select more than one choice. This will give us an idea of who we have on the line today so that we can make sure that we're kind of directing our questions to where you're coming from. So I'll give you a few more minutes on that poll. So I am going to close the poll and I will share with you the results. So it looks like we have a large number of higher education faculty members joining us, some industry professionals, and some laboratory coordinators, as well as some graduate students. This is a great mix, as well as some teaching assistants. So I'm glad to hear that you guys are all here today. I think you're in for a treat. So with that, we will move on. So my name is Dr. Natalie O'Neill, and I'll be the host of the webinar today. I'm the Higher Education Program Manager for Biohazard Score, a nonprofit organization dedicated to green chemistry education. The name of this webinar series has been updated to reflect the time that we are in, called Green Chemistry Connections. I think it's something that we are all striving for at the moment, in a time where we are having to socially distance ourselves. It's become so much more important to try to connect as best we can and keep working towards a sustainable future through green chemistry. Just some logistics before we get into the main event. We are broadcasting live and recording this session. Therefore, all attendees are in listen-only mode and all lines are muted. If you do have a question, please type it into the question box in your control panel at any time. We will respond to as many questions after the presentation as we can. The recording will be posted on the link you see in the welcome box and on this PowerPoint slide. Any supporting documents, such as the presentation slides, will be posted on this link as well. We just want to take a minute and thank our sponsor, MilliporeSigma, for their continued support and collaboration. MilliporeSigma's grant will allow Beyond the Nine to create a new inorganic chemistry resource guide and enhance its organic chemistry resource guide, which already exists, for universities and colleges looking to introduce green chemistry into their courses and programs. The new inorganic chemistry guide will begin development in July 2020 with the help and direction from the community. If this sounds interesting to you, please reach out to us, as we would love to have you involved in this process. You'll see here on the screen that our green chemistry experiments to undergraduate organic chemistry labs has been updated. It's been newly revised in 2020. And given the current situation, it was supposed to launch in March, but we have waited a little bit and kind of pivoted ourselves to expand the exploration of DOZN 2.0 into the academic setting. And so that guide will be launched in June 2020 through the Green Chemistry and Engineering Conference. This webinar is being brought to you as part of the Green Chemistry Commitment Program, which is a consortium program aimed at transforming chemistry education, expanding the community of green chemistry practitioners, growing departmental resources, and expanding the green chemistry practitioner community as a whole to improve the connections to industry and affecting systematic change in chemistry education. The program is completely voluntary, it's flexible for adopting green chemistry student learning objectives and promoting the work that you are currently doing at your institution that serves as a model for other institutions that are getting involved with green chemistry. If you'd like to know more information about this program, please email me directly. I would love to talk to you more about it. For those of you that participate in social media, please connect with us on Twitter or on Facebook. We would love to hear some live tweeting going on during our webinars, so join in if you would like. If you are joining us as part of a virtual class or event, please let us know in the chat box or on social media. We would love to know where you are joining us from so that we can share it with folks across the globe. In fact, we even have our beautiful and fabulous Juliana Vidal joining us all the way from Brazil to help us with the conversation on social media during the webinar. So please reach out to her through the discussion today. And thank you for joining us on this webinar and being part of the community. Without further ado, we have a wonderful webinar for you today on employing DOZN 2.0 in academic settings. Our first speaker is Dr. Edagande Pusami, also known as Semi, who completed his PhD at the University of Madras in India in 1982 in polymers chemistry and postdoctoral studies at the University of Illinois in Chicago. In 1988, he joined Sigma Aldrich as an R&D scientist and worked on many high-value products at various capacities. Currently, Sami is the Fellow and Global Manager of Green Chemistry at Millipore Sigma, formerly Sigma Aldrich, leading the Green Chemistry Initiative. Sami has over 35 years of industrial and academic research experience in developing new products, greener processes development, polymer processing, and greener manufacturing from laboratory to pilot plant scales utilizing green chemistry principles. Sami and his team developed the DOZN system, a quantitative green chemistry evaluator to calculate the relative greenness of chemical products based on the 12 principles of chemistry that he's going to talk to us about today. Sami has been absolutely instrumental in helping us understand how DOZN can be used in the academic setting. Our second speaker is Professor Irv Levy. He has been involved in the green chemistry as a focus of his career since 2003. Since then, he has introduced hundreds of students to the principles of green chemistry through lecture and lab, dozens of research projects, and his unique green organic literature forum that has empowered students to become ambassadors for green chemistry to thousands in high schools, museums, and other public outreach settings. In 2019, he joined the staff at the Department of Chemistry and Physics at Simmons University in Boston, and at Beyond the Nine, Irv serves as the director of the Green Chemistry Commitment in the Higher Education Program. Irv has been working with Sami and I to use DOZN in his courses, something I know he's going to tell you all about today. So without further ado, I'm going to move the controls over to Sami to take it away.
Thank you, Natalie, for the nice introduction. Good afternoon, good evening, good morning, depending upon where you are in the call. My name is Sami Ponnaswamy. I work for Millipore Sigma. I'm going to okay. Just 1 second. Okay, my title of the talk is DOZN 2.0, a quantitative green chemistry evaluator. So the DOZN 2.0 is a 12 principle based scoring matrix system. That DOZN is our trademark. We took the E out, so that's what that DOZN is. So somebody is questioning what we have a typo or something. Okay, excuse me. Not working.
Let me give you control one more time, Sami, and see if that helps.
Yeah. Let's see.
Still not moving forward, Sami?
No, it's not moving. Both the down. Okay, did you do it or I did it? I don't know.
I think I did it, so I'll move them ahead.
Okay. Outline of my talk is going to be how the DOZN 2.0 system works, how to apply the DOZN system with the product examples, and close it with an advantages, and also 2-minute video, demonstration video, how you can utilize the tool. And then Irv will take over how we can do this at this critical time of our situation as a virtual lab. Okay, can you move? Natalie, can you move the slide? Okay. 12 principles of green chemistry. I'm sure most of you know about this. About 20 plus years ago, Professor John Warner and Paul Anastas developed this. This is considered as the Bible for green chemistry field. You can see it covers the whole breadth of the sustainability. So we took this as our basis for our greener alternative program. Next slide, please. Yeah. So what we did was we developed algorithm for each individual principles, and then we combined to get an aggregate score of 0 to 100, 0 being the most desired. Next slide, please. Yeah. So if you look at the 12 principles of green chemistry, 6th principle talks about improved resource use. So like prevention, atom economy, use of renewables, reduce derivatives, catalysis, real-time analysis for pollution prevention. Those 6 principles are resource related. Then the next principle, energy efficiency, principle 6, that's a separate group. Then the remaining 5 principles talks about human and environmental hazards, like less hazardous chemical synthesis, designing safer chemicals, safer solvents and auxiliaries, design for degradation, inherently safer chemistry, and for accident prevention. So we group them into 3 groups. So we take that, next slide, please. Yeah. So we average the improved resource use scores, get the group 1 score. Next slide, please. Yeah. So energy efficiency. So the raw material input that contributes greenness in its is aimed at improving the energy efficiency. So it is a single principle, so it stays as it is. Next slide, please. So the group 3, human and environmental hazards, we average these 5 principal scores and take the group 3 scores. And next slide, please. Okay. We sum the group 1, 2, 3 scores. Yeah. And then we divide by 50. Why we divide by 50? We wanted to give the score from 0 to 100 scale, 0 being the most desired. But based on our experience with our DOZN 2.0 tool, we got the minimum, this score was like a single digit, the maximum was 5,000. In order for us to provide to the customer in a 0 to 100 scale, which is everybody will understand well, how green it is. So we divided by 50. So 50 is an arbitrary number to normalize the score to 0 to 100. So our DOZN system was verified and validated by third party, and also we published in ACS Sustainable Chemistry and Engineering Journal. Next slide, please. How to apply DOZN tool. Next slide, please. Yeah. So first step is you need to have a manufacturing information or the procedure to make chemical. That's a critical here in order to utilize this tool. Once we have that, our tool takes that information and then it takes from the STS and GHS information, safety data sheet and globally harmonized system information, and then calculate the score. So the data entry, the second step, and then there is a button store and score calculate, then the system will calculate. I will show you at the end, there is a video how this system works. Next slide, please. I'm going to show an example of a product, how we scored, how we improved the process. Next slide, please. Yeah. Beta amylase is an enzyme which is used to hydrolyze starch into sugar molecule. In our old process, which was 1950s publication, we have been using like over 6,000 pounds of sweet potatoes and close to 2,000 gallons of acetone at elevated temperature, boiling point, almost boiling point temperature, to manufacture this product. This has been a safety nightmare for our company. And also, we had another issue with this product. Only newly harvested crop only works for this process. And the yield was also low. And we wanted to improve the process. Two of our scientists took this process, this challenging process, to make it better. What they did was they have a home brewing experience. They looked into all the available literature, but they couldn't find better than one they are applying in their home brewing. The beer and wine industry utilizes the same kind of situation. You know, they take the grain or whatever, there is some polyphenolic compound comes out. Here also same thing, the polyphenolic compound, which in olden days, organic solvent is the easiest to remove the polyphenolic compound because we never thought about sustainability those days. So that's why those papers are published. We have been using it. So they looked into seriously how beer and wine industry addresses this situation. What they do is they apply polyvinyl polypyrrolidone as a scavenger, which that polymer itself is a biodegradable polymer. So it's a win-win thing. Our scientists worked 2 months in the bench, and long story short, they had a successful deployment of this process, and we scaled up. Now we reduced the usage of the sweet potato to 2,000 pounds, and we increased the yield more than double, and the solvent was completely eliminated. They made it as a water-based process using electrodialysis process. So the electricity use was minimized. I can show you the next slide, please. The score for this new process and the old process. You can see on the bottom right corner, the new process, the score is 1. We call re-engineered process. The old process was 57. And you can see that each individual principles, how much was improved. So like energy efficiency, 100% improved. Safer solvents auxiliaries, 100%. Waste prevention, 97. Atom economy, 93. So you can see each score. The principle NA is not applicable to this process. Overall, this process was improved 98%. I'll show a few more examples. Next slide, please. Yeah, these are some other products. Currently, we have about 50 products in this category of re-engineered product. Next slide, please. Okay, the advantages of DOZN 2.0. So the measurement is easy because we are using hands-on data, the manufacturing information. It's a straightforward calculation because STS and GHS informations are already there. And we are using 12 principles of green chemistry's benefits to calculate. And then we can communicate to the customers transparently why this product is greener. And the main thing here is data privacy. User can evaluate their process and products in a safe and secure manner. So the user's data, nobody can see it. It's only yours unless you share it with somebody. So this is a free web-based tool. It's available in our website, sigmaulrich.com/green, or you can, or DOZN. The DOZN system was verified and validated by third party and also published in ACS journal. This is the link here. And now I'm going to show you a 2 minutes video. This is sodium acetate, 2 raw material, 1-step reaction. How it's going to work. So first step is you go to sigmaulrich.com, go to the DOZN, launch DOZN tool, and one needs to register. First time user, register, and it takes 48 hours to get you approved. Once it's approved, it's your tool. You can go to the tool and you can start inputting your, this is a final product you are adding, sodium acetate. Then if there is no co-product, you just remove it and then start adding your reaction conditions, how long, how many hours, pressure, temperature, and then raw materials. Add each raw material one at a time. So you have another raw material to add. So you click that another window pops up. Add the acetic acid information. And then you are done with the raw material. Then here B score is a biohazard score. So you have to find that from the STS page. There is an information given on that icon. Once that's done, then you can go and save and calculate. So you can see the score for each principles. And then you can download you can see aggregate score on the left top. So 1, you can download to get the Excel sheet And you can cross-check your input also if there is an error or something. So thank you for your attention. I will take questions after the Irv's presentation. Irv is going to take over now to explain how it's going to work in academic setting.
Great, thank you, Sammy. And so I'm going to transition control now over to Irv so we can hear a little bit about how Irv has been using this for his teaching. So that was a little bit of a background from how DOZN work from Sami, but there is actually a whole webinar on that. So we will make sure that you get that information as well. It's a technical deep dive into it. This was just supposed to be an introduction to get you some behind the scenes information about DOZN. And now Irv is here to tell you about how he's using it in his undergraduate teaching.
Okay, thanks, Natalie, and thanks, Sammy, for getting us all on the same page as to what DOZN's all about. And I am going to talk a little bit about using it in the undergraduate curriculum. So as we think about that, we're sort of all wrestling with this social distance issue, right? I don't know about any of you, but are some of you having a weird semester? I'm waiting. I wish I could see the audience and hear your uproarious laughter at that question. But the question that we have right now, of course, is how to teach. We're spending lots of time on Zoom and other platforms, working with our students distantly. Thank you, by the way, for taking the time to be on this call today when you've already had all sorts of other reasons why people have been asking you to be on the computer. So I really do appreciate you taking the time to be with us today. But we're trying to figure out what to do about labs because, you know, if you're an English or a history professor or a philosophy professor, you may have a little bit of a different experience with doing social distancing in higher education than a chemistry, physics, or biology professor might have. So we're trying to figure out what to do about our lab experience. And of course, there's many different approaches. Virtual, well, I said versus simulated. Virtual and simulator are sort of the same things. And some of the things that some people are talking about is doing a marathon. Like, you know, maybe next semester, if we can't meet face-to-face at the beginning, maybe we can get together before the end of the semester and have students do like a marathon week of labs and do everything that week they would have done in an entire semester, versus just sort of pushing it off to the next semester. And some of us are even thinking about the possibility of doing labs at home. And so this is a creative moment for new possibilities that aren't currently in the curriculum as we try to figure out what to do with this unique situation that we find ourselves in now. And that's where the DOZN 2.0 tool comes in for me. It was a new experience for students who will get a deeper appreciation of green chemistry, including, I think this is very important, the ability to discern greener approaches and key areas for improvements in a process. That's where those scores that come out of the process really help. And a better understanding of the value of an SDS, and something that I don't know about you, but none of my students ever did until we got into the DOZN program, is the familiarity with a genuine industrial tool. Most of the time, our students don't actually use industrial grade tools, but DOZN is in fact an industrial grade tool, and it's freely available for the students to use, which is an unusual situation. So thank you, of course, Sigma and Sammy for making that happen. So there's some benefits to using DOZN. First of all, like I said, it's freely available. And I think this is a really important point. It showcases to your students that your personal focus on green chemistry is not isolated. It's not Professor Levy's the green chemistry geek. You know, there's a major corporation out there that's building tools to do green chemistry analysis, and I think that's really important. And it's a significant, non-trivial, team-amenable experience that can be facilitated in Zoom breakout rooms. So you could actually have a lab session on Zoom this way. Since there's no wet chemistry here, it's all hot chemistry, and taking the time to put things into the system. You could actually have your class break up into groups of 3 or 4 students and meet with them and then advise them as they're going through the process, because I do think that especially the first time or two that they use it, they'll need some advice and some hand-holding along the way. I know that as a faculty member, I've needed hand-holding along the way. I really thank Sammy for being the hand that I've reached out to many times to say, well, what about this? And he's always helped me out. Thank you, Sammy. So here's a problem that I would call with a very green lab curriculum. If your lab curriculum is kind of like mine, that's been carefully curated over a period of years so that all the experiences in it showcase green chemistry, that's a really good thing, but it's a problem because green chemistry is not a destination, it's a path. And if you're only presenting things along your path to green chemistry for your students, then they're never going to really have the experience to figure out how you got there. Especially important, they won't figure out how to make something else greener in the future. So students really have to learn something about the green development work that you've done. Otherwise, those green labs that you're creating for your students don't have quite the power that they would. So my case study in this is the synthesis of benzaldehyde, starting with benzyl alcohol as an oxidation. I like this one because all of our students learn about it in the chapter of the book that talks about carbonyl compounds and oxidation reduction reactions. And the textbook method to do this is to use pyridinium chlorochromate in dichloromethane. And it's not just the textbook method, it's actually sometimes the laboratory method too. Because there was a classic 1978 publication in the Journal of Chemical Education showing, actually based on work by E.J. Corey, showing how to convert a primary alcohol into an aldehyde using PCC. And reading this paper kind of gives me a little bit of goosebumps for a couple of reasons. One is because my green chemistry antenna are wiggling, but the other is because it reminds me of my college experience, because if you're a person of a certain age, you probably remember using 500 milliliter round bottom flasks and 100 millimole scale when you did your organic chemistry lab. I know for me, that was what we did. We were often working with what I would look at today and say a quart of this and a half pound of that. And that was just sort of the standard way that labs were done, at least when I was taking organic chemistry, which is about the same year as this paper was published. And so I looked at this paper, and of course, there's many other papers that have been produced since that talk about greener ways to do this, and using different catalysts, some biocatalysts and some interesting catalysts that are, nanoparticles and all kinds of interesting things that people have figured out how to do to try to do this reaction in a greener way. The method that I chose to focus on was selective oxidation using hydrogen peroxide as the oxidizing agent over a novel catalyst based on molybdenum, which is a hard word to say. At any rate, there's some interesting pedagogical advantages to this. First of all, it's a novel catalyst. You can't buy it. You have to make it yourself. So that does show students that that's what happens frequently in chemistry. You don't always just go and buy everything you need. Sometimes you have to make the things that you need. And this catalyst that we use is something that we have to make. It's super easy to make. It takes maybe 15 minutes, but for most of our students, it's the first time they've ever made an organometallic substance. And so it's just a really quick way to do that. And then they use their own catalyst to perform the reaction. And in performing the reaction, we tried to clean it even more from the way it was in the paper, because the paper that I started with used a 15% hydrogen peroxide solution as their oxidizer. And I just don't like using something that's that concentrated, especially when I'm going to reflux it with my students. So instead, we just use 3% hydrogen peroxide, just, pretty much grocery store hydrogen peroxide. And this catalyst, and by the way, another advantage is that it's a catalyst, which is one of the principles of green chemistry, is to use catalysts. And that compares to the PCC method, which used a 50% stoichiometric excess of the reagent. And so there's a number of advantages there. So what I wanted to do is walk through, we were showing you what sorts of things go into the analysis with that short video that played there. I'd like to show you how I collect the information that I needed. And as Sammy said, you have to start with a method. You have to start with an experimental method. And you're looking for all the substances and the masses, not volumes, but masses that are used. And you're going to want to get SDS data and supplier and catalog information. So for this one, benzaldehyde is the first thing that I looked up, which is actually, of course, a product of the reaction. Turns out that's one of the first questions when you go into the system. It asks you about the product. And so benzaldehyde is my product. As you can see, there's 11 entries for benzaldehyde in the Sigma Aldrich catalog. And so my method when I do this, and I don't know if it's the right method or not, Sammy can tell me later if it's not, but I just always pick the first one. And so, there's a whole bunch of options here. I just went to the first one there, the 418.099, and that would have been the option that I would have chosen. And of course, you can see on the page 2, there's also the link to the SDS. There's other data that you can gather here, like the molecular weight. And I create a little table for myself with these sorts of bits of information. We also have a template available that is going to, I think, be available for all of you, or else you'll get a link to how to get to it, too, which is another way of it being available, that you'll be able to gather the data that you need. And Sammy mentioned the biohazard score, the B score. This is an important thing and something that is not going to be found anywhere in the system. You're going to have to actually determine that yourself. And I love this for my students because they have to actually dig into an SDS. So all my students have seen SDSs before because they use them to look up, the basic hazards associated with substances before they use them in lab. And I need them to know what all of the, the signal words and the GHS icons and things like that. But now we're going to dig a little bit more deeply into it because it turns out that in this biohazard score, we're looking at the environmental hazard posed by the substance by looking at a few biohazard endpoints: acute aquatic toxicity and chronic aquatic toxicity. And you'll sometimes see those listed in an SDS in section 2 of the SDS as a GHS category number. Sometimes the category numbers aren't there, or they're there for something else, but they aren't there for acute toxicity or chronic toxicity. And so in cases like that, you have to actually go to the endpoints. And you get that information by looking later on in the SDS, usually in section 12.1. And if something has an acute aquatic toxicity of less than or equal to 1 milligram per liter, you would give it a 4. Now this is kind of a funny thing because the GHS system, the lowest numbers are for the most dangerous things. The highest numbers are for the more benign things. So category 4 is much more benign than category 1 based on its endpoint. However, in the B score, it's the other way around, that the worst substances have the highest numbers for B score. And so you'll get that information, and I'll show you an actual SDS as we move forward here. So this is again for benzaldehyde, and you see that it says acute toxicity, but that's not what we're looking for. We were looking for the aquatic toxicity. So it shows me an aquatic hazard here is acute, and it's category 2. So it's acute category 2, so I give it a B score of 3. And that's just going back to here. Acute category 2, B score would be 3. And I just playfully created something here called Levy's Rule of 5. You're maybe familiar with the Rule of 5 in the pharmaceutical industry, which talks about the likelihood of a drug having certain properties. This Rule of 5 is a really simple one. That is, I just noticed as I was doing this, that if you add up the GHS category and the B score, it always comes to 5. 2 plus 3, 3 plus 2, 4 plus 1, 1 plus 4. So it's a quick way to remember what your B score is without always having to go back to your sheet. And so that was the benzaldehyde. Now comes the bad guy. This is the thing that I wouldn't want to use and why I've never done this in my students' labs, because I just don't want to use pyridinium chlorochromate. Again, I get the information, molecular weight, the catalog number right down here, and then I'll click on the SDS to get the other information that I need. As I do that, I see, oh my, it's category 1 for short-term and long-term aquatic toxicity. Now, what if it was category 1 for one of them and category 2 for another? Well, you go with the worst category. You don't go with the average or the best. You go with the worst category. These both happen to be the same. So category 1 is the really worst category, and the Rule of 5 tells me the B score on that is going to be 4, and it is. That's the worst B score you can have. And then we're also using methylene chloride, and again, this sort of makes my my memories of my college years come back to me, because the amount of methylene chloride that's used is 170 milliliters per run. So each student group is going to use 170 milliliters of methylene chloride. You're going to bring that gallon bottle out, and people are going to be slopping it out into their beakers and into their round bottom flasks. We need to calculate the mass because the DOZN system needs to know mass, not milliliters. And so using the density, which I could have gotten from a number of places, but I found it here in section 9 of the SDS, comes out to 226 grams of methylene chloride per student group. That's an awful lot. The B score for methylene chloride, if you go here, there's nothing in section 2 that tells me about the aquatic toxicity. So we're going to have to dig a little deeper, and we go into section 12, and that's where you get the endpoint data, and it tells me that the data is 193 milligrams per liter for toxicity for fish. And also for Daphnia, it's 27 milligrams per liter. And if it's less than 1, it's category 4. 1 to 10 is category 2, and 10 to 100, no, category 3, 10 to 100 is category 2. And so that's why this comes out to be category 2, because we're in the 10 to 100 range here for the Daphnia toxicity. And then diethyl ether, and again, yay, we're using 250 milliliters per student group of diethyl ether. So if you've got 10 groups in the class, you're going to have 2.5 liters of diethyl ether, and everybody's going to float out of the room at the end of the day, probably. So back in the 1970s, when I was in college, people often had their coffee cup with them in lab when they came into lab. Today, we don't do that, of course, but back then it was quite common. And I'm aware of at least one person who, while they were doing an experiment with this much ether, they were very careful, but the ether that was in the room was dissolving in their coffee. And by the end of lab, they were just pretty much 3 sheets to the wind. So, I'm glad we don't do things that way anymore. Anyway, there's my diethyl ether. And I continue to gather all this data. And this is what I do for myself. I just put together a little table of the substances, the amounts. I have a density column in case I have to convert a liquid to a mass. And I have the formula weight in case I have to calculate the number of millimoles in order to determine something like the expected yield, which is something that we need to know. Okay, and now that I've got the data that I need, it's time to enter the product into the system, the information into the system. The first thing that we do is figure out the reaction conditions for the various phases of the process. And those things are each going to have their own temperature or pressure. So we have an addition, stirring, and extraction stage that I guesstimated would take about 2 hours. And this is the thing, as students are doing this, they're going to have to make reasonable decisions about things like this. I don't know if it's really going to take 120 minutes. It might take 90. Maybe it'll take 360. I'm sure you're aware that in your labs, you have some students that can do things very efficiently and others who do things less so. And so I tried to say, what do I think this should take? I thought it would take most of my students probably about 2 hours. And general conditions, no mention of vacuum or pressure, room temperature. And then there's another stage, is the fractional distillation. Sorry, that went by too quickly. The fractional distillation, and the fractional distillation stage, that's going to take maybe, now I would maybe overestimated this. I said 90 minutes, maybe it would take less. This is when they're going to be getting rid of the methylene chloride and the ether and ending up with their benzaldehyde coming over. And I did say that there was no mention of using reduced pressure here, but even though there was no specific mention of it, of course they're doing a distillation, so there's going to be some heating. So the temperature here, I just said we're going to use hot oil or electrical heating. Exact value is if I said I want to heat it at 70 degrees, 70 degrees for a certain period of time, then I can put that in, but I just know that I'm going to have to heat it. And so then we get into the raw materials. And there's a number of questions we're going to be asked for the raw materials. And I just want to give you some tips on how to answer those questions. One question you're going to be asked about a raw material is it waste? And the answer is only if it's discarded wholly in the process. If it's incorporated into the product in any way, or as an acid or base used to change the pH of the product, then it's not waste. So the answer is yes for a catalyst, unless you reuse it. If you're going to collect it and reuse it, then it would not be waste. It's also yes for something like an oxidizing agent. In this particular lab, that matters because the oxidizing agent's elements are not going into the product, but what it's doing is it's just changing the oxidation state of the product. And then there's category. If you say yes, there's categories of waste. And the categories are semi-solids, solids, and wastewater. So semi-solids are things that could be contained or used for land disposal. Semi-solids that are incinerated include all the organic solvents, and that's your most common choice. And then solid non-hazardous might be something like a drying agent. Wastewater, semi-hazardous, might be something like aqueous acids, bases, and salts. And then another question you're going to be asked is it renewable? I got messed up on this the first time I used the program because I was putting down yes for ethanol. And the reason I was doing that is because ethanol, I know, is a renewable material. We can grow it. But it only counts as renewable if the substance that you're actually choosing for a product number is from a renewable source. If the ethanol is from a petroleum source, even though it could be made from naturally grown sugar, it's not renewable. And so an example here is the substance that Aldrich markets called styrene, an interesting solvent. And you see this symbol, biorenewable, and there's a special green symbol down on the bottom. That one, the answer would be yes. But for my ethanol, it was just regular ethanol. It was not biorenewable ethanol, so the answer was no. Is it a solvent? The answer is yes here, only for organic solvents. And another sort of non-intuitive thing to me at times is that if you're using water as a solvent, then the answer is no, it's not a solvent, because the answer is yes, only for organics. Is it monitored has to do with whether or not you're using some kind of an analytical method to monitor the process in real time to alert of a spill or formation of hazardous chemicals. And by the way, this doesn't include using your students to watch the synthesis. So I know that during our labs, our students are standing there and they might even be taking TLCs from time to time, and they're supposed to be standing there making observations and writing things in their lab notebook, but that's not what we're talking about here with isn't monitored. So this method, this tool we're using is really an industrial tool, and it's not necessarily going to be always true, but the answers that you'll give will be answers that are completely obvious from a academic point of view. And so you'll have to work with yourself a little while and your students to get used to that. I really do recommend that you should do this a number of times yourself before you do it with your students. Another thing it's going to ask you is what's the substance being used as? And the options are as a reactant, which is an integral reagent that is incorporated into the product, or an acid or base used to change the pH. It does include things like oxidizers and unrecovered catalysts. Then there's a recovered reactant, a reagent that's used and recovered, like a catalyst if you recover it and use it for future use. An auxiliary is anything besides a reactant, so it's often things like solvents, wash solutions, and things like that. And a recovered auxiliary is an auxiliary that's recovered and reused. So for example, if you were working with an ionic liquid, I believe an ionic liquid would be considered a recovered auxiliary as long as you're keeping it to use again later. And again, I'm not going to belabor this, but you saw the graph that I had, the chart that I had before that has all the information. So now here I've got everything for the benzyl alcohol, the product, the mass, it's not waste, it's not renewable, it's not a solvent, its B score was 1. And then you click, where is it being used? Is it being used in the addition, stirring, or extraction part of the process, or is it being used in the fractional distillation? And the same for the PCC. And then we've got the other materials, the methylene chloride, which is part of the fractional distillation. It's also part of the extraction. And the diethyl ether, likewise, is in the fractional distillation and the extraction. Excuse me. And then there was a step in the procedure to filter it through alumina. So there's another step there that involves the addition, stirring, and extraction. And at the very end of the process, it's going to ask me about the B score of the product. And the B score of the product turns out to be a 3 for benzaldehyde. And the mass used here is 7.42, which was from the paper that I showed you at the beginning. That was the actual typical yield. And there were no catalytic steps and one synthetic step. It was not monitored. And next, you'll just save and calculate. And when you do that, you get the scores like Sammy was showing us. And its aggregate score is an 8 on that 0 to 100 scale, where 0 is the best score and 100 is the worst. And so we get an 8 here, which is, actually surprisingly good. I was expecting it to be kind of higher, knowing how nasty things like hexavalent chromium is, but that's what it turned out to be. And then you get the individual steps, the individual principles, I should say. And then I did the same calculations with my octamolybdate method, the one that I used the 3% hydrogen peroxide and our own homemade catalyst. So for this one, there are 2 stages. There's the preparation of the catalyst and then the reaction and distillation. And I did the analysis for the preparation of the catalyst, and it came out to be scores of 1.77, 0.88, and 3.32. Remember, that was compared to 60.46, 244.77, and 78.14 in the previous example. So since we're trying to go for lower scores, these are much better scores, and the students can clearly see that. And then the actual synthesis and isolation numbers I'm getting are also quite low, 1.77, 0.88, and 3.32. And so when you compare those to the catalyst preparation, you see that the first score, group 1, is a little bit better here than it was for the catalyst. Group 2 is the same, and group 3 is the same. And that was compared to much higher scores from the pyridinium chlorochromate method. So I would like to say that I've got some data there to show that that method clearly is a superior method. And I want to make a clear point here that I'm not trying to be critical of the classic authors. That author from 40 years ago was doing labs when things were done very differently. It was before people ever thought about doing things microscale, and it was before the words green and chemistry had ever been put together in a sentence in that order before. And even people who are really good at green chemistry did some funny things once upon a time. So one of the most important books to many of us in this field is Green Chemistry Theory and Practice by Paul Onassis and John Warner, which was published in 1998, as Sammy mentioned. But I went back and I found another paper that was also by John Warner and Paul Onassis from 1985. It was the Wittig reaction in the undergraduate lab, something that they worked on as undergraduate students themselves. And so this was published 13 years before their landmark book was published. And it's not a very green lab method whatsoever. And in fact, in 2019, another paper was published comparing that method to an olefin metathesis to make the same substance, which is stilbene, and shows it as a good method of comparing and contrasting a not so green method, which was created by the fathers of the field of green chemistry, versus a much greener way to do the same thing using olefin metathesis. And I think this would be an excellent student project to work on with DOZN after you have taught the students how to use it. So I'll hand control back over to Natalie, and then we can answer any questions that you might have. Oh,
great,
Natalie.
Irv. Thanks great, Irv. Thanks so much. So I'm going to take control back over from you, and we will take questions. So there have been questions coming in, and I will get to those. We are going to turn on our webcam so you can see that we are people on the other side here. We know that everyone is searching for human connection these days, and so we are going to turn on our webinar cams. So hi, everyone. So glad that you could join us today. We do have the first question coming in, so I'm just going to go back up. So Sammy, I think this question comes to you. This approach looks quite similar to that made by the eco scale. Is there any comment in comparison between both of these? Oh, Sammy, I think you're muted. Yes, I can.
Can you hear me?
Yes, we can hear you now, Sammy.
Yeah. So I'm not familiar with the eco scale, so unless I know, I cannot comment on that.
Okay. If we have time, we will come back to that one.
I can check and get back to you.
Okay, great. So another question comes in that, is it possible through this metric to compare, for an example, a continuous flow method with a batch one, or a two-step process with a one-pot process?
Yes, we can do a step-by-step. The only thing we launched this tool for anybody to use almost a year ago, May 6th, 2019, as the web-based free tool. We didn't realize at the time the step-by-step calculation. We are looking into how to add into DOZN 3.0. Each step will scores, but right now we have to input all the thing together. We get a score. If you want to split it, you have to split each step as a separate product. Then you will get the score. That's the disadvantage we noticed, and we are collecting information for our next upgrades.
Great, Sammy. Just like green chemistry, we're always a work in process, right? Greener,
Yes,
not
yes,
green-ish.
yeah.
And it's good
It's
to know
not green.
All right.
tomato
Green.
is the way.
Thank you.
So another question coming in is, this process applies to raw materials themselves, but not for finished formulations. It would be great to develop one for finished formulations. So I think, Sammy, do you want to clarify there a little bit? I think there's maybe a little confusion.
Yeah, so this is only for the finished. The DOZN tool works as long as you have a manufacturing information. So say you are making a sodium chloride. If you know how to make that process, then you can score it. If you don't have, then you cannot score it. Use this tool. The manufacturing information is critical for the tool to work.
Yep, so we kind of translate that a little bit into the academic language. As long as the student had a procedure and they had an assumption of what the yield would be, or in the template, academic template that will come to you as a follow-up to this webinar today, we have recommendations of, if a yield is unknown, it would be a general rule would be between 70 and 90%. So as long as you have the synthetic steps and processes to get to a product, you can run the DOZN score for any product that has the synthetic steps, either published in the literature, or if it's something that you would want to even try yourself, an adaptation of something that is in the literature, you could compare it and see, would the changes that I make actually make this process greener overall? And is that, am I being clear in that, Sammy and Irv? Is that what you've experienced?
I can just jump in on that. Also, that's, the thing I was saying earlier about having a very green lab curriculum. Your students don't know where it came from. So I think that that's a really important thing, is to show them alternate ways that things could be done. And then if they use a tool like this, they can actually literally calculate that your way is better. Or maybe they'll also see, by looking at the details, that there's some things that still could be made better. So you may have gotten something better than it was before, but like I said, green is a path, not a destination. So they might say, well, could we work on this number that's kind of too high? And the answer is, of course, that's perfect. That's exactly what we want the tool to be used for.
And I want to add one more thing. Once you make the calculation, you can see the Excel sheet where it's contributing. You can go and modify your process to improve the scores.
Mm-hmm.
All right, great. So I do see that the person that asked that question is going to clarify a little bit. So we'll just jump to another question for now as we get some clarification. So here's a question about the B score. Is the B score undervalued or poorly weighted?
No, if we say the only disadvantage is some of the new product, we may not have the B score. So in that, we go as a default of a higher score. So other than that, all the established materials, the B scores are available. But for the new process, it takes time to get those things for the STS, GHS people to get into that information. So.
Great. So another question coming in is, are there any examples of reactions with a score greater than 50? I'm still astounded by the relatively low score of the PCC reaction.
Yeah. Well, I would love to hear the answer to that too, because I was also astounded by that.
So could you repeat the question again, please? I didn't get it.
What's something that has
So have you, in your time in the industrial setting, Sammy, seen scores that are greater, bigger numbers in terms of higher overall aggregate scores? So something that's higher than something in the higher ranges. So I would say those are probably examples of what you showed us of the re-engineered products.
Mm-hmm. Yeah, like a beta amylase, 56 versus 1. 56 was the old process, 1 was the re-engineered process. So I don't know, am I clear?
I think so. I think it's just that, those of us who are used to academic chemistry just don't really have a good feel for what happens in the industrial side of things.
Yeah.
And
I
so
understand that. because in industrial it's completely different because the volumes are much bigger and but it works proportion in the either small scale or large scale, the scores comes relatively closer because everything is adjusted to it.
All right, great. So we do have just some clarification on the question about formulation that came in. And so this is, for example, in personal care formulations, we combine green chemistry ingredients and process the formula so that it's needed. We would need to calculate the value with a modified tool like DOZN 3.0.
Yeah, the DOZN 3.0 is in progress right now. It's not in existence, but we can do that. Yeah.
Okay, so stay tuned for DOZN 3.0.
Yeah.
In that
Yes.
time. So I do just want to clarify, there is one more question coming in about the B score. So the B score is very important with respect to health and safety. Its importance is given in mass rather than toxicity.
Say that again. I'm not quite sure what the question was.
Yeah, could you read it again?
Sure. So I think the question comes around the B score, and maybe we could just run through that quickly again about what the B score means. So B score meaning biohazard score. To get that biohazard score, the students or whoever is running this process would need to go to the SDS to get that information.
Right.
And that's how you calculate the B score. But in putting the product information into DOZN itself is also pulling GHS information based on the product number that you put into the system as well. So there is definitely toxicological information going into the DOZN system in regard to not only the B score, but also what the system is pulling from behind.
Yeah, the system pulls all that physical hazard as a health hazard, all those things. But B score, we need to enter ourselves because there's a biohazard. You have to go to the STS page, section 12 point something. It's given on that our tool. There is a drop down menu there. I mean, there's icon there. You hover the icon over there, then the table will show up exactly what's in the STS page. So
I'm not sure if this is the question that the person's getting at, but this is one that does occur to me from time to time. Since all that information is already in the system, why doesn't the system just go ahead and calculate the B score for me? Because I'm just looking for the GHS categories and so forth, and so the system could do that too.
It's a good question. We will ask our third-party vendor because that's where they recommended to go with. They don't want to, because some of the B scores not available, that those things constantly updated. So we want to, at the given time, people go and look on those things, then that's the thing they came. But we will look into our 3.0, how we can improve that.
Well, I can say, as much as I wish that the system did that at times, I'm sort of glad that it doesn't also, because as a pedagogical tool, I think it's better for our students to dig through the SDS and actually find the data and see what the data means. And so I kind of like that.
Yeah, because they recommended like that. Everyone has to go through that because it takes a little longer. I mean, maybe another 5 minutes extra, but it's worth doing. People will understand.
Right. And I have to tell you, after showing my students, I had some advanced synthetic students this past semester at Simmons University who were using, who learned about the DOZN system by viewing a webinar that was a previous green chemistry connections webinar related to the system. And they learned about it from that and from a little bit from me. And then I put a question on our midterm where people could get some bonus points by using the system. And I made the comment that, you know, this is an awful lot of work for not very many bonus points. So I almost tried to scare them away from it, but almost everybody did it. And I had one person say to me, she really wanted to do it because she wanted to have the experience with this industrial tool. So I think our students kind of really like it.
Okay, that's good. Good to hear that.
That's great. So on that note, just by looking at the time and all of the greatness that you have shared here today, I am just going to wrap up our final slides. And we also do have one more poll for the audience. And so I am just going to shut off my webcam now because the poll will take over the screen as well. So I am going to say, it is nice to see you all.
Bye, everybody. Thank you for being part of this.
Yeah,
yes.
Thank you.
And so thank you for joining us so much. If you are teaching online right now, we do have a list of virtual resources that is curated by us and resources from our partners. We are happy.
What happened?
We are happy to have you add to that list. So if you are creating resources, just kind of like the one that we have shown you here today, and that we have a student template and kind of walking you through the steps as well, we would love to add to that list. If you do have ideas for more Green Chemistry Connection webinars, we would love to hear them. And we would love to have you connect with us on social media. We are on all of those platforms. And so I am going to launch the last poll that we have. It's a thank you for joining us, and tell us what you would like to see next. Great, so I do see some answers coming in. I'll leave that poll open for a few more seconds. Wow, we're really in competition between two areas here. All right, so I am going to close the poll, so get your voting in there. All right, so I'm going to close the poll and I will share the results with you now. So it was a tight race for a while between virtual labs and more green chemistry connections, but now it looks like we've got a tie between more organic chemistry resources, which we do have a ton already currently on our website, and I'd be happy to share those with you if you do reach out, but more green chemistry connections. So we'd love to have the community help us in building out these connections. We really like them to be valuable to you. So please do share your ideas with us and come back and connect with us on our next one. So stay tuned with us through social media and also through our newsletter to hear about the next webinar coming your way. So stay well out there. All the best. Thank you for joining us.
Thank you, Natalie and team. Bye.
Bye-bye.